next Tuesday. It's a week from today. So, if you're contemplating this, that's the last day. Don't miss the last day, because if you do that, and you take the second exam and you're not real happy with it, and you come to me and you say, I want to withdraw, I will not withdraw a student because you don't think you're doing well. That's not a valid reason. So nobody asks any questions up until next Tuesday. And then everybody asks what happened. So it's an important date. I'll probably put this one up every lecture between now and June 4th. All right, today's lecture, I like this one. I think it's kind of fun. The book calls this chapter The Language of Chemistry. I kind of just call it ions and compounds. So, let's see where I saw. So, last lecture was on the periodic table. We talked about elements and some of the properties of elements. And the lecture before that was on types of matter. We did matter and energy, which was, we talked about matter in general and pure substances. So in completing the talking about pure substances, we talked about elements. Today we're going to talk about compounds, and in talking about compounds, we're going to talk about ions. So we're going to start with good old, what's his name? Antoine Lavoisier. If we remember all the way back to chapter 4, Antoine Lavoisier was responsible for something. Anybody remember? It was a law. It was one of the laws. We'll give the clues in a little bit. So it was one of the laws. One of the laws of conservation. We got two choices.
Conservation of mass.
Mass. So Antoine Lavoisier was responsible for the law of conservation of mass. His version of it was that essentially the mass of the reactants in a chemical reaction was equal to the mass of the product, so that the mass, total mass, was preserved. He was also responsible for a paper called Methods of Chemical Nomenclature, which was his logical system for naming substances, and it's the basis of how we name compounds today. Lavoisier was a busy, busy guy. Now there's an organization, I mentioned, this came up on one of the slides the other day. The acronym is IUPAC, International Union of Pure and Applied Chemistry. They are an international body that makes up rules. They have a commission on the nomenclature of inorganic chemistry. Obviously, they have a commission on the nomenclature of organic chemistry as well. They published a set of rules for naming inorganic compounds in 1938. They revised and expanded it in 1940, and it hasn't been changed since. So, what I learned in high school and college, and what I taught in college way before you, and in some cases your parents were born, hasn't changed. So this is the same thing. Inorganic compounds usually don't contain the element carbon. In some cases they do. They're not based on carbon. Carbon is not the primary element. We're going to talk about 5 different kinds of compounds. Binary ionic compounds, binary molecular compounds. Binary means there's 2 elements that make them up. Ternary ionic compounds and ternary oxyacids. There are 3 elements that make them up. Ternary meaning 3. Binary acids, like binary ionic compounds, is actually a specialized version of binary ionic compounds. Again, 2 elements. And binary acids are always talked about in aqueous solution. Always dissolve in water. So I'm going to talk about each one of these types of compounds. So, a binary ionic compound is made up of 2 elements. One is a metal and one is a non-metal. Metal being from the first 2 columns in the periodic table, groups 1A and 2A. Possibly the transition metals, and the non-metal, which are the elements more towards the right-hand side of the periodic table. A binary molecular compound is made up of 2 non-metals. Carbon dioxide, carbon and oxygen, both from the right-hand side. Hydrogen, well, not hydrogen. Silicon dioxide, sand, is from the right-hand side. Get into more detail. We'll get into a lot of this tomorrow with the naming. Ternary ionic compounds, 3 elements, at least 1 metal and 1 non-metal. And we'll just leave it at that. We're going to talk about ternary. Binary acid is a type of binary ionic compound where the metal is hydrogen. So it's hydrogen plus a non-metal in a binary acid. A ternary oxyacid is a type of ternary ionic compound, again, where hydrogen is the metal. There's a non-metal and oxygen. Aqueous solutions produced when a compound dissolves in water and is noted by this symbol AQ in parentheses after the formula for the compound. So these are all definitions or true and false questions that pop up on that second exam. So here's the chart from your book. Inorganic compounds and acids, ionic compounds, binary and ternary, it just means 2 elements and 3 elements. Molecular, 2 nonmetals. Aqueous acids, binary acid, which is hydrogen plus a nonmetal. A ternary ternary oxyacid, which is hydrogen, a nonmetal, and oxygen. Hydrogen, a nonmetal, and oxygen. All right. So we've talked about compounds being ionic. Well, what's an ion? An ion is an element or a group of elements that have a net electrical charge, either positive or negative. Positive ions, cations, we have monoatomic, which is single metal atom with a positive charge, or polyatomic, which is the group of atoms bound together with an overall net positive charge. Negative ions or anions, monoatomic, single nonmetal atom with a negative charge, polyatomic, a group of atoms bound together with an overall net negative charge. So, do you have to memorize all of them? No, because they're all in the inside back cover of your book. We've got the monoatomic cations, let me get to the naming system now. Monoatomic anions, polyatomic cations, where the book only lists 2, and I don't even count hydronium. The only one that I really talk about is ammonium. And polyatomic anions are here. So the names, the formulas, and the charges are in the book. But you're going to have to take my word on this again. It's a really good idea to have a little plastic ruler or a little something for the straight edge, so that when you're looking things up in this back of the book, you can read across and make sure that the formula that you're reading and the name match up. Because a lot of these names look the same. There's chlorate, chlorite, hypochlorite, there's nitrate and nitrite, there's sulfate and sulfite. 1 letter difference. Now, these are just simple inorganic compounds. Wait till you get into your career and you're dealing with pharmaceutical products, where all the names look the same. And you've got generic names and you've got brand names. So, just look at, Viagra, sildenafil, Cialis, tadalafil. Big names that don't make any sense because the only place to look them up is in the physician's desk reference that lists all the pharmaceutical products and gets updated all the time. And they're long names and they look the same. And you don't want to be messing that up. Yeah. You really don't want to be giving them Viagra when they need something that just kind of looks and sounds like Viagra. They might not be happy, or they might be really happy. You just never know. But it's important that, and you have to trust me on this one too. This will happen on the second exam. I'm going to give you the name of a compound. I'm going to ask you to write the formula. And even though it's very simple and the name only has 2 parts, people are going to get the second part wrong because they didn't read it right on the test paper, or they read one thing on the test paper and they went to something else in the book. It's a little scary for me grading them because the information is right there, but some people are going to get them wrong. So we've got to concentrate and focus, and a little ruler will help. So here's the book's chart of ions. Cations and anions, monoatomic, 1 atom, polyatomic, group of atoms bound together. Cations positively charged, anions negatively charged. All in the inside back cover of your book. I'm not going to give you an ion that you cannot look up in the back inside cover of your book. Because where would you look at it? monoatomic ions, metal ions. With metal ions, we have two different naming systems. The stock system, which is the IUPAC system, says that the way you name a monoatomic metal ion, right, it's just an element with a positive charge, is the name of the metal ion plus the word ion. So, sodium plus is sodium ion. Magnesium plus 2 is magnesium ion. Sometimes metals have several ions with different charges. Iron has, there's iron plus 2 and iron plus 3 because of the nature of their electrons. In those cases, we include the positive charge in the name, so iron 2 ion or iron 3 ion. Now, just speculating, why do you think it's really important that iron has two different ions? What do we know about iron in the human body? Where do we find iron in the human body?
In the blood.
In the blood. And where exactly in the blood? In the red blood cells. And where in the red blood cells? In the hemoglobin. And the job of hemoglobin is what? It's to transport oxygen from the lungs to the various body tissues in order for those tissues to perform whatever biochemical reactions they need to perform. And hemoglobin is a relatively large molecule, and at the center of it is an iron. And sometimes it's iron 2, and sometimes it's iron 3. And compounds that are made, compounds that contain a triply charged ion are typically red in color. And compounds that contain an iron 2 ion are typically blue. Does that sound to make sense of the body? Why venous blood is blue and arterial blood is red? Because the arterial blood is carrying the oxygen. The iron in hemoglobin is +3. When it gives up its oxygen to the tissues, the iron goes to +2. The blood cells essentially turn blue, go and back to the heart to be pumped out through the pulmonary artery, the only artery in the body that carries venous blood. The pulmonary vein being the only vein in the body that carries red blood, oxygenated blood. So, only place it's reversed is between the heart and the lungs for when you take physiology. So, sometimes metal ions have more than one state. Then we have something with metal ions, and only with selected metal ions. When there are multiple ions, we have a Latin naming system. The lower charge ion ends with OUS, and the higher charge ion is the IC ion, and it has a Latin base to it. So iron becomes ferrous, Ferrous, and the iron 3 becomes ferric. We have that with iron and lead and cobalt and mercury. Iron, lead, cobalt, mercury, let's see if we have any of this, copper, and tin. You don't have to write these down to memorize them, they're right in the back of the book. So the Latin system, only those 6. Only those 6. And I will test you on stock name and Latin name for those 6. So I expect you to be able to look it up in the back of the book and copy it onto your test paper. I don't think that's being too demanding. In fact, most of what we're going to do in the next 3 lectures really boils down to finding something in the book and copying it onto your test paper. Or finding something in the lecture notes and copying it onto the test paper. Read and copy. Here are a list of some common cations, positively charged ions, and how they're written. Aluminum, barium, cadmium, calcium, cobalt. Here are the 2 cobalts. Copper, here are the 2 coppers. Chromium, hydrogen, 2 irons, 2 leads, lithium, magnesium. So when we've got 2 names, this is right from the book, and this is right in the inside back cover of your book. Cobalt 2, the lower charge, OUS, cobaltus. Copper 1, the lower charge, cuprous, cupric for the Latin system with iron, copper 2. I'm going to come back to mercury, which isn't on this table. So, non-metal ions. The stock system is the truncated name. Truncated means kind of chopped off of the non-metal element plus the suffix IDE. Bromine ion minus 1 charge is bromide. Chlorine, chloride. Iodide for iodine. Nitride iron is N-3. Oxide is O-2, phosphide, phosphorus, and sulfide. Monoatomic anions. The Latin system for anions, there aren't any. There is no Latin system for anions, just for those 6 cations that we named about 2 minutes ago. So, if I give you a true and false and it talks about the Latin system name for non-metal ions, it's going to be false because there are none. Nice. And you can use the periodic table if you were asked to, and I'm not going to ask you to because you can look this up in the back of the book. But if you needed to guess what the charge of a monoatomic cation or anion was, you can determine that by the group numbers. We're going to skip these kind of pink ones in here. Group 1A typically forms positively charged ions, single positively charged ions. Group 2A typically forms doubly positively charged ions. Group 7 forms singly charged negative ions. Group 6 doubly charged, and Group 5 triply charged. 3A aluminum is the only one we're really talking about. Boron are triply charged positive ions. And kind of, if you recall from the periodic table, as we move down these groups, 3A, 4A, and 5A, the elements become a little bit more metallic in nature, so tin and lead, each of which has a +4 and a +2 ion, are down here. but you'll be able to look those up. Tin plus 2 is stannous, S-T-A-N-N-O-U-S, because it's the lower of the two. Stannic, 4 plus, those are the Latin names. Or tin 2 ion and tin 4 ion, lead 2 and lead 4. Pb stands for plumbus and plumbic. Plumbus, plumbic. The only one that's tricky is mercury. Mercury has both a +1 singly charged cation and a doubly charged cation. The doubly charged cation looked just like all the others, Hg2+. Mercury 1, I remember what's the other thing that's unique about mercury, or almost unique? It's a liquid. It's a liquid in its normal state. It's the only metal that's a liquid in its normal state. Bromine is a non-metal that's a liquid. But mercury doesn't form mercury +1. It pairs itself up. So 2 mercury +1s, 2 mercury atoms, ions, forms a diatomic ion. Doesn't exist as mercury 1 ions this way, it exists this way. So the formulas always reflect this, which we will talk about again tomorrow when we learn about folding. Polyatomic anions. These are the ones where some of you are going to make mistakes. I'm sorry if you are. Because I'm going to say chlorate, and you're going to write, instead of writing ClO3, oh, I can use a smart board where I can underline this. Instead of writing this formula for this ion, you're going to write this one. Or I'm going to ask you for hypochlorite, which is this, and you're going to write either one of these. Because somewhere you're going to go, those are pretty close. He must mean this one. Same thing with nitrate and nitrite, sulfate and sulfite. There's even another one here, perchlorate. What's this? So you've got 4 with chlorine and oxygen that look kind of the same.
How would you ask the question?
I would say, what is the chemical formula for sodium hypochlorite? So I'm going to write it in words, and you have to write it in symbols. And people will pick the wrong ion, because this is an A, and this is an I, and this is a hypo, and this is an I, and this is an A, this is a per, and somehow people think that they're all kind of interchangeable. And they're not. They're all different. Nitrate and nitrite. Nitrate and nitrite, sulfate and sulfite. They're different. And they're different. They have different chemical properties. One might be okay in food, one might be really toxic. One might be really toxic and still be in food. sodium nitrite, which is put on meat in order to keep it red. Did you know that? Did you guys know that beef is typically treated with sodium nitrite, which is also called, it's pink. The salt is pink. And it's sprinkled on